Sir, welcome, sir. Good morning. Good morning, sir. Can you hear us? Sir, your mic is muted. Please unmute your mic.
I think so. Good morning.
Now you are audible. Yeah, good morning.
Okay.
Sir, with your permission, I would like to introduce you to the participants in a few moments.
Thank you. Get going.
Thank you. Dear participant, it's my proud privilege to introduce to you Professor Surya Kumar Maiti, Professor Emeritus at IIT Bombay, Mechanical Engineering Department, IIT Bombay. He obtained his BE Mechanical from Burdwan University in 1970 and he was a gold medalist. He completed his MSc from Birmingham University in 1973 and subsequently did a self-guided PhD at IIT Bombay in the year 1980. He was a postdoctoral fellow at the prestigious Cambridge University from 1981 to 1983 under the guidance of a renowned professor, Professor Michael Ashby. His experience, he has worked as a research fellow in Central Mechanical Engineering Research Institute, Durgapur, India, from January to July 1971. After his post-graduation, he worked as a design engineer in Tata Motors, Jamshedpur, India, from 74 to 75, and joined as professor at IIT Bombay from May 1975 and worked there till December 2009. From December 2009 to 2012, he was offered a prestigious G.K. Devrajulu chairship, and he was a chair professor in mechanical engineering and worked for 3 more years after his retirement. It seems that IIT Bombay was not ready to relieve him, and he was offered further the post of Emeritus Fellow from 2012 to 2018 for long, 6 years. In the meanwhile, he was also visiting professor in Mechanical Engineering Department at National University of Singapore in the year 2010-2011. He has many honors to his credit. Some of them I am reading for you. He has got Excellence in Teaching Award in 2006 at IIT Bombay, and he is a very popular teacher in the Mechanical Engineering Department till today. He is fellow of the prestigious National Academy of Science of in India, fellow of American Society of Mechanical Engineering, and I must mention that he is only the 6th Indian to get this prestigious fellowship of ASME, USA. He is fellow of Indian National Academy of Engineers and a reviewer for several reputed international journals. His areas of interest and research include fracture mechanics, finite element method, boundary element method, slash methods, and component health monitoring. He has developed many courses and taught the courses during his stay at IIT Bombay, like solid mechanics, strength of materials, finite element and boundary element methods at postgraduate level, stress analysis, fracture mechanics, fatigue fracture failure analysis, pressure vessel design, advanced finite and boundary element methods, and the like. He has also, to his credit, an NPTEL course on advanced strength of materials. He has published widely and has more than 150 papers in international journals and conferences of repute. Towards the end, but not the least, that he has authored a book on fracture mechanics, fundamentals and applications, which comes from a reputed Cambridge University press. In December 2020, Stanford University published a list of world's top 2% scientists from various fields of engineering, and Professor Maiti's rank there is 942 in mechanical engineering as the subject area. Please welcome my guru, teacher, and philosopher, Professor S.K. Maiti. With this brief introduction, sir, may I request to take over the session and start with your first session.
Thank you, Professor Naik. welcome all the participants of the course. I'm really very delighted to come to participate in instructing some of the rudiments of the topic that he has mentioned, damage tolerance, a new design strategy. As I understand that all of you are faculty members and some are research students, so all of you are mechanical. That's a good thing to know. And you know what my objective is to stress, first of all, what is damage tolerance design and how are you going to really be benefited by understanding this damage tolerance concept. So I'll get started. I'll just let me project my PPT. I have to share, no, Sachin?
Yes, sir. You have to press the second key for, on the left side of the red button.
Oh, that Google button, right?
Yeah, left on the left side inside the Google recording, Google Meet. There is a red button at the bottom. Go to the second button after that red button on the left.
Okay, that three thing. Okay, that
No,
arrow.
next to the three dots is the one arrow. Click on that.
Yeah. Okay, on that. Yeah. Entire screen, right?
Yeah, entire screen.
Dilip Patel, please keep your camera off.
Yeah, share your entire screen. Yes.
Once you do that, you have a window in which you see all pictures. Click on that window. And then share button will get activated. It will turn orange. Then you click on share button.
It says share and cancel करके करता है क्या cancel?
No, you click on the picture inside that new window which has appeared.
Okay.
After that, the share button will get activated.
Yeah.
And now click on the share button.
कर दिया.
Yeah, it is coming.
It's coming. Yes, it's coming.
Yes, sir. Thank you.
Thank you.
Yeah, make it full screen after it starts coming.
Stop presenting. क्यों कहता है? So I just make the full screen.
Yeah, but I don't know why. Yeah, you can make it a full screen.
Yeah.
Sir, sir, you park this window.
Yeah.
You park this window.
Yeah, it's okay.
This is it.
Now see, okay?
Yes, sir. You can make it bigger.
Yeah.
So that it fits the screen.
That's okay. Yeah, yesterday we did that. So it should, where is that scale?
It is
Oh,
on
yeah.
the top.
No, it
On
is,
the
it is,
top.
it is on
Yeah,
the
yeah.
top. Yes.
Yes.
It's okay?
Little more also will do.
Okay?
Yeah, perfect.
That's good. Thank you.
Thank you, sir.
You know, all of us are engineers, and that too mechanical engineers, or one of the important job that we have to do is the designing of machine structure, plant, air, I'm sorry, aircraft, ships, and many things of the type. Even let's say that a system, a power plant, and whole aircraft. So all these are our duties. And if you really try to look at the core aspect of design, I just like to put it as a simple thought that as a designer, what we do is that we try to find out the action of the loading on the structure, then down to the elements of the structure. And our responsibility is to make sure that the maximum stress or strain in the whole component nowhere exceeds the permissible limit. And therefore, you see that we generally try to consider that design is simple equation that actually sigma is less than equal to the stress permissible. And if we try to make it needle point based design, then we write that the maximum stress in the whole component should not be exceeding the permissible limit sigma y yield point of the material. So that has been the case. This is our traditional strategy. Unfortunately, what happens that this strategy has some pitfalls. Like that, you see that this approach, it does actually have some limitations. That material has got to be homogeneous, free of defect. This puts a limit on the utilization of materials. Further, this does not keep any room for accommodation of any error that can be there or defects in the material. And these defects can come up during manufacturing, it can come up also in service. So this approach, it does not really give us any room for accommodating all this. And I think let me stress these points, these are very important, that this defect in the material, it can come up in the parent material, it can come up during manufacture, it can come up even actually during the service life of the component. So therefore, these are actually obvious, they will come. And in fact, according to STM, 90 to 95% of the component are not subjected to static loading, they are subjected to cyclically varying loading, and they are actually designed based on some approaches. But then, you see, the question is that even if we consider designing based on this approach, one point which is quite clear that many of the components are subjected to cyclic loading, and our design is that if the component can withstand about 1 million cycles, that's fine. So that the load it can withstand, that will be the permissible load. But then the question is that even after the expiry of that life, it does not become useless. It has some utility. And if we wanted to see that, can I go on using that defective component or damaged component for some more time, then the question is how long I can make use of, and how do I go about finding out that question? There is no answer in the classical design approach that we take. Now, I just wanted also to illustrate and give you some points for thinking. I'm sorry, what is this? Why is that it has become?
You can just increase the size again by pressing
No.
that plus button.
Okay, okay. Now I think why it is actually.
I also don't understand. Yeah.
Now you see that why it has become.
Page view. Sir, click on the page view, the fourth button on
Okay, on the top.
page view. Single page.
On the left, single.
Single,
page, yeah.
single.
Yes.
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 That's okay.
Yeah.
That's what it is. It's this whole nonsense has come. Now let me see. Okay. Sorry.
No problem, sir.
Yeah. So, look at this manufacturing defect. When welding, the welding is a manufacturing operation. During welding, certainly defects come up in the joint and welds. Then, if we consider bimaterial composite plate, then obviously, it is going to have some disjoint, or there will be some disjoint, and then there is loss of continuity of material. So these are actually some of the defects which comes up during manufacture. Then coming to in-service defects, gear tooth. You see, the gear tooth is continuously subjected to loading, which is fluctuating from maximum to zero, again back to maximum. So this sort of thing, that these are loading which comes up in service, and therefore they are going to lead to damage origination, and hence we have to ask the question, how do I ensure the safety of this component at that point? And obviously there are many failures that has come up because of this in-service defects. Turkish airline, which failed in February 2009, there a design blade disintegration took place, and that originated from a crack and then finally led to catastrophe. And there are many examples which are recorded. I just also like to talk about them a bit. See that computer solder joints, and nowadays computer manufacture, there are thousands of solder joints, and these solder joints, because of the temperature going up and down, there are actually defects which come up, and therefore this also leads to failure because of the cyclic variation of load. Then one example, US flyover bridge failure, Brazil oil platform just crumbled down. So these are all actually originating from some defect which came up during the service of the component. So crack may not have existed to begin with, they developed and grew gradually, and finally they lead to fracture. So therefore this failure, so the catastrophic, it comes up because of that. So therefore now the question is, some of the propagating crack also, it has been actually noted in the mechanical applications, particularly pressure vessel, nozzle junctions. That is one crucial location, and if they are working at temperature variant condition or actually load fluctuating conditions, they also give rise to crack and they gradually propagate. Now the question is, this as a designer, we have to make sure that even if they are propagating, we should be able to do some preventive measure, or we should be able to actually at least calculate what is the degree of safety, reliability of this component at that point of time, and if it is going to last for some more time, how long it is, and how do you actually get that? So these are actually some of the concerns. So classical designs, they are not really in a position to give you the assessment of safety after the system has been used in practice for some more time, and it cannot give you also the how much of load at that point it can carry. So therefore it cannot also allow you to calculate the load capability, and also how much time we can go on making use of it. That's what also some question it cannot answer. Now the question is that as designers, as a user of the system, they would like to know that how much is the safety available at this point of time and how long we can go on using it. So these are some of the questions, we cannot answer from the classical design considerations, and therefore there are gaps. The problems of power plants, some of the things which are also very important for consideration. See, power plants, thermal, hydel, nuclear, offshore rigs, they are subjected to fatigue loading, thermal loading, and deleterious environment. They work in environment which also have effect on the structure, and they also will try to increase the sort of damage because of their presence. So these are some of the issues, which cannot be addressed by the classical design. Then coming to think of it, another issue which is also you must really recognize, that nowadays you see everybody is interested in trying to use less material for the same machinery, and they should be able to take more load. So therefore, you see that everybody is interested in trying to make the design so that it becomes actually lighter, but then it can take more load, it can give more life. So in the process, you see that the common tendency is to use the stronger material, lighter material, and in fact, unfortunately, nature is not kind to us that if, okay, you make material stronger, so it actually brings in some problems with it. They are actually your less strong material that in general have little bit of plastic deformation capability or ductility, and which can really give some benefit. But then as you make the stronger material, they are actually brittle, and then therefore you see the problem increases. So nowadays you are using in aircraft all the lighter alloys and then stronger alloys, and they are really brittle, and therefore again you see problem increases. So therefore you are given some benefit, but then at the same time you also have to face some deficiencies. So this is how it is, and there are so many examples. Fluctuation of loading in shipping industry, they are also subjected to corrosion plus fluctuation in loading. Chemical plants as such, they are subjected to fluctuation in loading, thermal loading and corrosion. So all these problems are existing. Microsystem, nanosystem, cracking due to thermal fluctuation, that I was mentioning, that in the case of solder joints in the computer, there are many solder joints, and these are subjected to thermal cycles, and therefore they also give rise to damage and then finally leads to failure. So therefore the question is that many deficiencies are there in the classical design, that sigma maximum stress is less than the permissible value sigma y is actually having that difficulty. So this is the problem, that the old classical approach to design suffers from this. So therefore, there is a question that how do you overcome this? And obviously, that new concept has to come up, and that new concept, fortunately, it has come up with the development of the fracture mechanics. So that fracture mechanics, it has finally given rise to a simple equation of the type similar, which looks similar to that classical design equation. It is K less than equal to some critical value of K. So if you again try to put it in a slightly different manner, in the design, what is that you do? You really try to take the structure and its loading and different conditions under which it is operating, and under those circumstances you try to calculate the parameter sigma, which is, it could be actually maximum principal stress, it could be maximum shear stress, or if it is strain-based, maximum strain and all that. So therefore, classical design equation looks like that. And this fracture mechanics also has given rise to an equation of the type K is less than equal to Kc. So just spend a minute on this. You see that in classical design, you have actually been designing since your engineering days. So therefore, you try to know the subject of stress analysis, strength of materials, and then you come up with lots of understanding, and then you are in a position to calculate sigma, which is the outcome of the loading and geometry of the system. And on the other hand, you see that you have to also get the value of this permissible stress, sigma y, which actually we try to find out through experiment. So therefore, you see the things that are needed, you ought to have knowledge to find out sigma in the component of a system, and then you should be able to get the material property, which is sigma y, experimentally. So therefore, you see, this is how the whole situation is involving the knowledge to calculate sigma, and on the other hand, it also requires system to measure the permissible value of that parameter. So therefore, you can now try to extrapolate that if you are going to have the new design strategy, which is based on fracture mechanics. In fact, actually, fortunately, it has come up to similar looking equation, that K and Kc. So K is the factor or parameter which is actually determined by understanding the subject of fracture mechanics, and obviously you would also have concurrently some experimental procedures to find out the permissible value of that K. So this is how it is. So therefore, this, if you are trying to say that damage tolerance based design, so it is really based on that damage detection and also calculation of the parameter associated with the damage in the structure, and then make sure that that parameter is less than the permissible value which is determined experimentally. So this is how it is. So therefore, you can actually imagine that in this course of new approach to design, how are you going to actually be exposed, and these are actually this is the background which you should keep it in your mind, and you should try to recognize the fact that the lectures will be given to make you aware of the parameter K, and at the same time determination of that value experimentally. And of course, you will be also given some examples of applications. So so the questions, I would like to then sum up by saying, therefore, that one should say as a participant what you should be doing. How has this parameter K evolved? That is first thing. So even actually when you have gone for engineering, they make you understand what is stress, and then how do you calculate the stress in the components of various geometry. So this is actually the way it will be gradually going. Then what is the effect of reactive plasticity? You know that obviously materials are all not perfectly brittle. There is some plastic deformation capability. So therefore, you will also have the understanding, will be given the subject to understand how this reactive plasticity is actually accommodated. Then this K parameter, that sigma like in classical design, how is this K parameter determined, and then methods of measurement of critical value of this K, and the propagation problem, of course, we are also going to look into that. If a crack originates in a component, it is going to propagate. So if we know the path of crack propagation, then we can take measures to prevent its propagation. So therefore, you see that how is this crack propagation route can be determined. So these are some of the things. So that's how actually this course is going to really bring you out all the issues gradually. So that's all. Now let's try to actually get into some understanding that you may have had, and then new understanding, new things that we are going to actually bring in. So I will actually get started with that part. So if you just consider, basically that how this subject has originated, it is also having a history. So material scientists were looking at material, it is nothing but actually an assemblage. It is assemblage of atoms interspaced, and they are interconnected by or interacting with each other. by interatomic forces. So therefore, when you consider a material to be a picture of just atoms placed in space and they are interconnected, and one can imagine that as if they are interconnected by springs like the interatomic forces, that if you try to just actually view it, you can consider that as if, that look at this. This is how it is, that it is like atoms interspaced and they are actually interacting with each other with interatomic forces. So we have, they used to represent by this spring bringing in, so therefore that's how they are there. So when you are trying to pull a sheet of material, then what you are trying to do, you are trying to actually increase the interatomic spacing, that A, and then the resistance that's going to come up is going to be sigma, which is on the vertical axis, and A is the actually interatomic spacing distance A, and the deformation, which is nothing but current spacing minus the original spacing, that is going to vary like this. So therefore, when we try to actually pull the materials, then you are trying to increase the interatomic spacing, and therefore the resistance is going to vary like this. It is sort of approximated as a sinusoidal curve, and therefore it gradually increases, it reaches the top value or maximum value sigma c, and then subsequently with the increasing distance, the resistance actually reduces and finally it gets separated. So that's how the material theory, and material scientists looked at the whole phenomena of deformation like this. And therefore this, which can be written like this, that sigma is varying in a sinusoidal form, and therefore if you are trying to do this, how much of work that is done in increasing the interatomic spacing, so that is W, and it can be calculated sigma dx, and the distance is the half wavelength is lambda by 2, that is actually distance you have to work out, and it gives you that energy required is nothing but sigma c lambda by pi. So that's the energy. Now you see, the question is, once you have done this much of energy you have given as input, what does it do? When the material gets separated, that energy, where does it go? See, the energy just like that cannot be actually eaten up. So what it does, that if you take a material of unit area, as you pull it, it breaks into two pieces. If you just try to pull a chalk piece and then try to go on pulling it, it gets broken into two pieces. Material is brittle here. So therefore, that after the failure, two surfaces are created. You see that new surfaces are created, and indeed that for creating new surface you need to supply surface energy. So therefore, if each area is one unit, then and gamma s is the specific surface energy, then obviously to create to break the element, you need 2 gamma s is the energy. So therefore, that where from this energy came, that the work done when you are pulling it, you are putting in energy into the system by that work done, and when it fails, that work done is really what is going to supply this surface energy. It goes as surface energy. So the energy which can be considered to be strain energy of deformation, and when it breaks, that strain energy of deformation goes to supply the surface energy. So one form of energy gets converted into another form, and that's how the new surface is created. So therefore, you see that for energy conservation, the work done is equal to surface energy, and therefore, by making some approximations about the sigma as modulus of elasticity multiplied by strain and all that, and we can do little bit of manipulation, and finally you see that if you make use of that W equal to WS, finally it gives you that strength, that maximum tension that is required is calculated at E into gamma S by A0. What is this? E is the modulus of elasticity of the material, gamma S is the specific surface energy per unit area, and A0 is the initial spacing between the two atoms. So this was actually first calculated by material scientists. What is the strength of a material, theoretical strength of a material? So any material, you can calculate the theoretical strength. and using the normal data for this surface energy, and this critical strength comes out as modulus of elasticity by 10. And modulus of elasticity, most of the material, for the engineering construction material, in fact, the strength going to be in the range E by 100 to E by 1000. Look at that. Theoretical strength is E by 10, but then actual strength of the material is E by 100 to E by 1000. So it is 10 to 100 orders less. So this is actually, this model which was initially given, it really finally got entangled in these questions. And finally, that if you just consider few materials, let's say steel ultimate limit is about 400 to 1800 MPa and E is 2000 GPa, then the range of actual strength is E by 5000 to E by 250. So therefore, you see, that is much less than the theoretical strength. Aluminium, if you take ultimate stress is about 100 to 500 MPa and G is 70 GPa, and if you see the actual strength range, it is E by 700 to E by 140. Theoretical strength is E by 10, but these are actually E by 100 and more. So therefore, you see, the question is that what happens? That theoretical strength does not really correspond to the actual measurement that we see. So therefore, that became actually a concern that what is this? That actual strength is much less. It remained as a question, and therefore, people, scientists again started searching for the answer, and therefore the first answer that was actually given by Griffith, and he said that, although we consider material to be defect-free, it is actually flawless, but in actual practice, there could be some defect in the material in the form of, cracks, disjoints, and this elliptical, cutout and all that. So all that, again, that concept was brought in, and what they said is that although we apply sigma at the loading point, in actual case, that the stress which exists at the tip of the stress concentrator, a crack, it is much higher. So it is actually stress concentration factor which amplifies the stress, and that's what is acting, and it really actually fails the material. It really actually breaks the material much lower level of external load. That could be the. So that was one explanation that was given, but then it was not very acceptable. It had pitfalls, because we generally consider design at the macroscopic level, not microscopic level, and this model was really brought in to be effective at the microscopic level. So this mismatch didn't allow this theory to be acceptable for a long time. So it didn't go further. And then you see the Hooke's law is generally applied at the macro level, not microscopic level, but these models are actually at the interatomic spacing level, so they are also not acceptable. So all these things are gone, and finally, that new ways of thinking came up, that how actually can we really make something which is not this, which is something different. Just 1 second, I have to get some more slides. It's okay, visible? Is it visible? Participants?
Yes, sir, it is visible.
Yeah,
Make it bigger.
I'm just trying to. Okay?
Little more big, you can make maybe. One more time.
Okay?
Yes, sir, thank you.
Good. Thank you. So, this sort of explanation that was not acceptable by the community, the scientist community, and then it had its actually end. And then you see a total different approach to consideration of failure came into being. I think I would like to stress that this is the actually state where this damage tolerant design concept, or actually fracture mechanics concept, started evolving. It's around 1920, that people started thinking. This thinking was actually at the beginning of the 20th century. And therefore, this is something, which came up in about 1921. So 20th century beginning. And therefore, this is something I think, again, I would like to stress upon that please look at actually the way scientific development has come up. So, that Griffith was the first man who started actually thinking the failure of the material. It's not really that it is stress reaching a critical value or strain reaching a critical value, and it is different. He started thinking of that this material failure, it should be actually looked into within the scope of first law of thermodynamics, energy balance. That if some failure is taking place, it's really giving rise to transformation of one form of energy into another form, and therefore this energy balance concept, and that should be the basis to understand failure. So therefore, Griffith actually gave the energy balance approach to failure, and which really made the beginning of this fracture mechanics. So what happens, you see, that if you try to take a plate flawless, then you have stress sigma everywhere, and if you just have a defect inside the material, you see that defect is of size 2a, and when you are pulling the material, then it is common to expect, it is logical to expect easily that obviously that the material above and below the crack, it becomes a shadow region. It does not actually get loaded. And therefore, when you have a plate without any crack, it is uniformly stressed everywhere. But when you have a plate with a crack and it's loaded, it does actually have some area which becomes a shadow area. There is no loading on it. And therefore, what he said is that this shadow area, it does not have any energy. Energy means when you load a component, it has strain energy per unit volume. But when you have this, you have some bit of material which becomes load free, and therefore it does not have any energy content. And therefore you can just think of it that as the load increases, crack extends, and therefore the size of this shadow region increases, and therefore the material, quantum of material that is becoming energy free is also increasing. So therefore you see that this crack extension, it does have two effects, that it does increase the shadow area, and therefore the material that is losing energy is becoming increasing, and at the same time what you are having also simultaneously, as the crack extends, the surface of the crack increases, and therefore it becomes actually, it requires more energy for creation of new surface. So therefore you see that in the material, as you load it, it is strained, and as the crack extends, you are creating surfaces, and you have to supply surface energy on the other hand where from it comes, because it is actually creating some stress-free region, and therefore that material becomes stress-free, and therefore it loses the strain energy. So therefore you see the two energy forms are at play during this crack extension, that material is actually losing strain energy, and at the same time it is actually supplying the surface energy. So therefore he made it very simple that crack propagation takes place in the presence of two forms of energy. One is strain energy and another is surface energy. And therefore when a crack is extending, it should be able to supply the surface energy required per unit area of new surface to be created, and obviously that energy comes up from the strain energy of the material. You have strained the material, strain energy you have given in input, and as the crack extends, that strain energy is getting actually converted into surface energy. So therefore, he said that two forms of energy are at play during the crack extension. One is strain energy and another is surface energy. So therefore, from the understanding of energy, energy cannot be destroyed. So therefore, obviously it is strain energy is the actually source of energy, and surface energy is the sink of energy. So energy from the source to the sink is going during crack propagation. So if crack propagation is to take place, your energy supply, that means strain energy availability, for crack extension must be more than required energy for the surface creation. So therefore, he propounded that the rate of release of surface energy, rate of release of strain energy is the actually to be the source of energy, and rate of absorption of surface energy is the actually your requirement. So therefore, sink of the energy is actually surface, and the source of energy is the strain energy. So driver is the source of energy, and sink is the is driven. So therefore, this is the two things. So it is from the strain energy to surface energy conversion is the crack propagation process. So that's how the whole concept changed. No question of stress and strain. It is more of energy balance, thermodynamic energy balance. So therefore, people started looking at crack propagation is nothing but actually thermodynamic process of energy conversion. And therefore, you see with all the calculations that if you say delta U is the strain energy change per unit crack extension, and if you say that's energy required per unit crack extension delta Ws by delta A, then this is the condition of unstable crack propagation. If your availability of energy is more than the required, it is going to lead to unstable crack propagation. And these calculations, finally gave the critical stress capacity of a material, and it was of the type, you see that sigma is equal to sigma CR, which is nothing but E2 gamma S divided by pi A square under root. So therefore, this is the form of new expression. It had actually same the similar structure as in the classical interatomic spacing model, and this became the actual starting point of calculating fracture strength of a material with crack, with defect. First time it is with defect. So therefore, it is that sigma CR is E2 gamma S by pi A, and it was written as EGC by pi A. And GC is nothing but fracture resistance of the material. And what is its value? It is nothing but 2 into gamma S, where gamma S is the surface energy requirement per unit area. So Griffith, in fact, showed experimentally, he did experiment, and nobody will believe without experiment. In science, you see that you cannot just like that propagate, you propound a theory and people will accept it. You must also show experimentally. And therefore, Griffith did experiment, and finally, he showed the relationship is that sigma C is proportional to 1 by root A. So therefore, that's the reciprocal relationship. And in fact, he did experiment with glass rods, many experiments, and then finally said that whatever theory says it is going to come, which is where it is coming up. So that's how it became the starting point of finding out the critical load capacity of a structure in the presence of crack. So it is actually a fantastic stage of development of strength of materials or material science, and this is how it is. That this, let us reflect on this theory, scope of Griffith theory. You see, this relationship is important. It gives safe load level for a given size of damage or crack in a component. So therefore, for the first time, you are in a position to calculate the safe load capacity of a component with damage in it, crack in it. And alternatively, it can give the tolerable crack size for a given load level on the component. Yeah, this is also something, please note that it gives you critical load capacity once you know the geometry of the structure and the crack size in it. Alternatively, if you are having a structure and you have loading, then you can ask the question, how much of crack or damage can be tolerated? That's what is damage tolerant design. You see, how much of damage defect can be tolerated in a given structure with geometry and the loading. So that is the basis of this damage tolerant design. And in fact, it became a fantastic stage of development, and it really opened up the process of damage to aircraft design, all airborne structures, which were or space-going structures, space-going vehicles. Structures are actually all the time designed based on damage-tolerant design. So that's how it is a very important development, and therefore you must understand the varieties of problems that can be there and how do you address them. So that's what it is. That this theory was, it's about 1920-21, this theory was given, and it is just after the First World War. And then the limitations of this theory. What are the limitations? This has come, it's nice, it's hearing nice, it can also give clarity in applications, no difficulty. But that the question comes up that there are also deficiencies. What are the deficiencies? It cannot be applied to ductile materials. That Griffith considered the situation where the material is brittle, no ductility. So therefore, that no plastic deformation, and therefore it's okay, because mostly, the newer materials, they're highly brittle, and therefore it was very nice. So the drawback is that it does not get easily applicable to materials with plastic deformation capability. This is one shortcut. And then, he considered the crack to be in the orientation perpendicular to the loading direction. So this is called opening mode of crack extension. It cannot be applied if the crack is at an angle to the loading direction. It cannot be applied. And the other thing, classical understanding of failure of material is based on stress strain distribution in the whole body, and in the presence of a crack, this theory, energy balance theory, does not give any importance to the stress strain distribution at the tip of the crack, where classical people would like to take it up that there must be some typicality in the distribution of stress and strain at the point of the crack, near the point of the crack tip, but it does not give any importance to it. So that was something. So these are some of the shortcomings of the model, and then gradually, people try to look into overcoming these problems, and that's how the subject has all developed. Now, first objection that plastic deformation cannot be taken into account, that was attempted, and Irwin or Rowan, these are the two scientists who looked into it. So let's see that what Irwin or Rowan stated. So Irwin or Rowan stated that, you see, that again we go back to the model that was considered about the material failure. So when you are trying to talk about a material with a crack or a structure with a crack, as you load it, in general what happens that stresses are very high, stresses and strains are very high near the crack tip, where stress concentration prevails, and therefore material, rather than just actually failing, it will give rise to, first of all, plastic deformation. So plastic deformation will take place, and then probably it will propagate. So therefore, you see, before the crack propagation, you have deformation energy or strain energy in the body. Then if you create the new surface energy is also there. But then, before it becomes actually surface, that material will deform plastically. So earlier we are just considering that the strain energy gets released, it goes to the surface for the creation of new surface. Two forms of energy were there, but they consider that it's not that way. You see that you deform the material, and therefore you are inputting strain energy in the body, and then near the crack tip, before the propagation takes place, it gives rise to plastic deformation. And in plastic deformation, you see, it is a irreversible process, and it absorbs some energy. So therefore, before the crack propagation, plastic deformation will take place, and therefore some amount of energy will go into that zone which undergoes plastic deformation. So therefore, you see that rather than having two forms of energy during crack propagation, strain energy and surface energy, there must be the plastic deformation. So therefore, three forms of energy comes into picture during this crack propagation, and therefore the model that was given by Griffith, it was amended. What Irwin and Rowan say, that you see that your strain energy is the supply of energy or source of energy, that's fine. But then when you are creating new surface, you see, you just have the surface energy dispersed for unit crack extension, but you must also have plastic energy supplied. You see, as the crack propagates, before the crack propagation or surface extension, it gives rise to plastic deformation. So that energy should also be supplied. So they assume that the plastic deformation energy is constant per unit crack extension, and therefore if that is the case, then we can actually write the energy balance, the equation slightly modified. Left is strain energy per unit crack extension, right is surface energy per unit crack extension, plus plastic energy per unit crack extension. So if we assume that plastic energy per unit crack extension is gamma P, and T is the thickness of the plate. So therefore, you see that the earlier equation was pi sigma square AT by E greater than equal to 4T gamma S. But now they amended that there should be also plastic energy per unit crack extension. This is 4T multiplied by gamma P is the plastic energy per unit crack extension. So that's how this amendment was given. And in fact, actually the new equation damage tolerance relationship is this, that sigma critical is equal to square root E gamma 2S plus 2 gamma P divided by pi. So, in the earlier, this gamma P was not there. Now this gamma P has come up, and therefore that is the amendment. And in fact, when it is a brittle material, then this gamma P, the plastic deformation energy is very, very small, and surface energy is the stronger part of it, and therefore this equation was valid for brittle material. But if it is actually ductile material, then gamma P is much higher than gamma S, so therefore the equation. So that's how this became the amended equation, and in fact it did actually it did solve the problem, and it made it acceptable for people. So that's how it is. Now, coming to think of it, that the other questions, that objections or other the shortcomings that people raised, that it does consider the crack to be loaded normally about its own plane, it can be different. So therefore, we must actually answer that question. And similar, it is just one loading. The loading is perpendicular to the crack plane. But if it is actually different, if it is, let's say, shear loading, if it is at an angle, so those are the problems which couldn't be answered by the theory that was propounded by Griffith initially. So again, it became a problem. So this is the story around 1920s after the First World War. But then you see that this question cannot be resolved, that if the crack is otherwise at an angle, then it cannot be answered. And obviously, this thing actually was unanswered till about 1950s. See? Imagine 1920 was the Griffith theory, but then this objections that actually stood for about 30 years, and then it could be actually relooked, and then it could be finally answered again back around 1959-60, around that time. So therefore, that's the new approach, and in fact, that could actually overcome some of the objections that were raised, and therefore this is in fact considered to be the beginning of fracture mechanics. So this is it. So we would like to actually get started with this. And this was actually something which was answered by Irwin and his approach. So see this crack, imagine the crack to be like this, that you have a component which is loaded perpendicular to its plane. So this is, that trying to open up the crack faces. So this is called opening mode of crack extension. The crack faces were trying to separate out, increase the distance, and therefore this is mode 1. And then, that he not only identified this sort of classification, this is actually mode 1 crack, and he was also the person who could find out that everybody says that we must understand the stress and field around the crack, and therefore he was able to solve the problem of elasticity of a component with a crack in it and the stress and field around it. So that stress and field of the crack around it was actually obtained by him, and this is the form of the crack. So sigma x is the stress which is acting actually parallel to the x direction, the crack direction itself, crack plane direction. It has a form of that. It has one parameter which is k subscript 1, mode 1, and then that theta function. It is function of r and theta, distance from the crack tip, and theta angular disposition. So this is how, and then these displacements around the crack tip, and this parameter K1 is given actually by the load that is applied remotely and the crack size. So therefore, this stress field, you see, it has, please have a study on the form of the stress field. It is K1 by root 2 pi r. K1 is a parameter which is related to the crack size and the external load applied, and R function, R is actually there as it is inversely proportional. It is proportional to 1 by root r. So as R reduces, stresses increases. Stress actually becomes infinity at R equal to 0, and R theta function is there. And in fact, it is the first term of the infinite expansion. First term is R to the power minus half. Next term is R to the power 0, R to the power plus half. This common difference in the exponent is half. So this is the form of the stress field. So this is how it is. Then the loading that he considered, he considered that in practice, the loading can be in 3 fundamental modes. First one is opening mode, where the loading is acting perpendicular to the crack plane. Then he considered that second way of loading, it could be parallel to the crack. You see, this is actually shear mode loading. Loading top is parallel to the crack plane, and it is trying to actually mode, it is actually considered mode, shear mode. So this is how it is. And again, he analyzed the stresses and displacements and gave the value of this parameter K2. And so these two modes are there. And the third mode, that it is this one. It is twisting mode. It is shear, torsion mode they call it. This is torsion mode. It can be twisted. And this twisting mode, is considered mode 3. In the torsion, if you have a shaft with a circumferential crack and it is subjected to torque, it will be this mode of loading. So therefore, here again, he tried to find out the stress field and the full expression. So that's how it is. So let us, get little bit comfortable about what are these modes, where do they occur, and why should we bother about it. You see examples of mode 1, mode 2 mode. Particularly, mode 1, if you think of any linkage mechanism, see in the railway, by the side of the railway track, you will find that some links are there, and then they push it as the carriage goes, and then when they are actually pulled and pushed, they are subjected to loading in the axial direction. Similarly, pressure vessel, if you are trying to think of a pressure vessel under internal pressure, and if you have a crack in the axial direction in the material, that is also subjected to opening mode. Beam, if the beam is subjected to loading, let's say cantilever beam, and you have a crack perpendicular to the axial direction, so that is also subjected to opening mode. Rotating disc, think of a rotating disc, the grinding wheel or any high-speed shaft. If you have just think of a thin sheet rotating, then obviously, the centrifugal forces, they are trying to develop stresses both in the circumferential and radial lines. So if you have a radial crack in a rotating disc, then the tangential stress, circumferential stress is going to open up that crack. So that is actually mode 1. So therefore, all that in the mode 1 crack example is there. Now coming to think of mode 2, shearing, punching blank. When you are trying to actually take a thin sheet and you are trying to actually do the punching operation, so when you push the punch enters into the material and it just tries to take a bit of material with it. It goes in the direction of movement, and finally it gets separated from the remaining stock, and then it is actually going to lead to separation. And therefore, you see, this crack which is propagating as the tool moves, it is a mode 2 crack. That part that bit of material is being pushed into the material, and therefore that that cylindrical cell area, is going to shear. It is going to the bit of material below the punch is going to just actually go perpendicular to the sheet, and then it gets separated along the cylindrical surface, and that is actually mode 2 crack. Similarly, in case of rivets, keys, and beams also, if you look carefully, in the case of beams, you have done shear force bending moment diagram. So therefore, if you remember that shear force bending moment diagram in the case of beams, then obviously, shear force is acting on every section. And therefore, for every section there is shearing force, and that shear force, if a crack is there in that orientation, in the depth direction, it is undergoing actually mode 2 loading, and that's it, how it is going to have in beams. Then in the case of shaft, if you have a shaft, and then if you just think of a keyhole is made, or rather actually a notch is made around the circumference, then when you are twisting it, that one portion of the one side of the shaft and the other side of the shaft, they are trying to have displacement in the circumferential direction, and it is really giving rise to mode 3 loading. And therefore, these are actually practical examples. There are many examples, and these are certainly practically occurring, and then in general you will have problems of not one mode, it could be more than one mode. So mixed mode problem. So therefore the study is very, very important. So what we will do, so let me just see what we can take it up. The other issue that I would like to discuss now, that therefore this active stress field was determined, and therefore the objection that was raised by the people was eliminated. But now, the question comes up that in science particularly, that if you try to say that a new theory has been given, then people who just like that in a totally new theory has been given, people in general would expect, until and unless you are in a position to link the new theory with the existing theory in some way. So that was actually something very good. So the person who really developed this stress, K is called stress intensity factor. The stress intensity factor based approach was given that this K is an important parameter for failure, and therefore he said that that when you are trying to think of the increase in loading, that K parameter is related to the loading. So as you increase the loading, stresses also increases, and then from common sense you can say that a typical level of loading is leading to fracture, and therefore it means that typical value of this K parameter is reaching at the point of failure. So that's fine. But then the question is, that people also found that energy balance concept of Griffith, that is a very sound concept, and therefore you cannot just like that say that it is, that stress intensity factor is the parameter which is leading to failure. And it was very important to establish that this reaching of critical value of this parameter K is also linked to the conditions that Griffith actually gave rise to. That at the point of unstable crack extension, the energy release rate is reaching a critical value, and which is equal to the energy required for creation of new surfaces. That was also a very sound concept, and therefore people started thinking of that, yes, until unless you have given a new concept that K is the parameter which is really leading to the very critical state of stresses, and it is leading to failure, that was okay. But then you see that you should not just like that overcome that theory that Griffith has given, that energy is also a concept. So therefore, can you really prove that this K reaching a critical value leading to fracture is equivalent to availability of energy critical volume of energy, critical quantum of energy that is required to create new surface. So you are given the question that you must establish that how is this K related to the strain energy release rate of Griffith. That strain energy release rate of Griffith is nothing but 2 into gamma S per unit crack area X. Therefore, that should be also established. So Griffith had to actually answer that question. I'm sorry, the Griffith energy release rate has got to be calculated from the stress field that was determined by Irwin. So he did, and fortunately he cracked that thing, and then he showed that yes, you see that this K, which is reaching a critical value at the onset of crack extension, indeed it also ensures availability of critical energy for the creation of new surface that has been given by Griffith. So that is actually something which we would like to see, and it is all mathematically established, and we like to actually consider that. That how do we get the relationship between strain energy release rate G of Griffith to stress intensity factor at the point of onset of crack extension. So he took up the case of mode 1, and in fact, what he considered is that this is a picture which must consider that we have a crack of size A in the plate, which is uniformly thick plate, and it is subjected to remote loading sigma. And when we try to have sigma, then this R, it has its coordinate, its origin is at the crack tip. So if we try to see the variation of the stress which is acting in the y direction, sigma y stress on the crack line, it varies like this, K1 by root 2 pi. So it's a variation, square root variation. As distance increases, it reduces, and at R equal to 0, stress is infinity. You see that at the crack tip, stress is infinity. The mathematical solution is giving you the picture that at the crack tip, stress is infinity. So you cannot just apply the classical theory that stress reaches a critical value leading to fracture. That cannot be answered. That is invalid. But then one thing is there, that this sigma y stress, if you try to plot it against R, it's actually going in proportion to 1 by root R, and therefore this is the variation. So it is very high at the crack tip and gradually reducing with distance R. And therefore you see that this sigma y stress on the crack line is given by this K1 by root 2 pi R. So theta equal to 0. And as the crack extends, this look at the picture at the sketch at the bottom. So as the crack extends, you see that your crack was initially of size A, but now it has got extended by delta A small distance. And therefore, as the crack extends, you see this portion from the original crack tip to new crack tip, stress becomes 0. It becomes stress-free. So this loading on this area which is created by the crack extension is 0, opening stress is 0, but at the same time you see that crack faces has opened up. It was closed here, but then now it has opened up by this distance which is equal to V on each side, therefore 2V. So therefore you see that when your crack is extending, this portion of the material is actually getting load free, so it becomes stress free. And in the process, it also gets displaced by this 2V at the distance xi from the crack tip. So therefore, you see that as the crack faces are opening up, they become stress-free, and therefore, material is actually the load-free, it's displacing, and therefore one can calculate that if it becomes actually opened up by this sort of displacement, then can we calculate the energy that is actually work done? The crack at a point xi, it was actually 0 displacement before the crack extension, but after the crack extension, it has become 2V. So therefore, load is reducing 0, but then displacements become 2V. So therefore, if we plot sigma y versus the gap, it is actually going like this. So therefore, the work done, so crack is opening up and it is becoming stress-free, so therefore how much is the work? So crack extension is leading to really crack opening and becoming stress-free. And therefore, if you want to actually make this extended crack back to original crack size, you have to close it, and you have to close the crack faces by distance 2b as given by this solution. The B solution is there at the top. So that solution is at the top, and therefore, if you are trying, just a minute. Yeah, you see what I'm saying, that as the crack is getting load free, it is giving the displacement that much. So therefore, the load at each point, some load is there, which is dependent on sigma y, and it gets opened up. It becomes opened up by this much. So therefore, one can calculate that if you want to close the crack, then what we have to do, we have to pull the two crack faces by loading sigma y on the crack faces, put that displacement to 0. So the work done in closing the crack is nothing but the energy which got released during extension from the original crack to the extended crack. I want to actually repeat this point. What I am saying, this is called reverse argument, although it is irreversible process, but then Irwin made it as actually reversible process, that if the crack got extended from A to A plus delta A, then you have this displacement and it has become stress-free. But if you want to actually bring the extended crack to the original crack, that is A plus delta A to delta A, then I have to actually eliminate this opening. I have to make that 2V 0, and therefore the work done in closing the crack is given by this. This is the energy which is required in closing the crack from A plus delta A to A. And all this calculation was done by using this solution. And finally, you see that this became as delta A tends to 0. So it becomes that energy that is required, that is there, work done per unit crack extension is given by K1 square by E. And that is nothing but strain energy release rate of Griffith. I think this is also a very important point. Please understand that the work done in closing the crack per unit area is equal to the energy which gets released as the crack extends from some size to another size. And that energy per unit crack extension is given by K1 square by E. And in fact, that is nothing but that Griffith strain energy release rate G. You see, this is a very important stage of development in fracture mechanics, that Irwin was able to really link the Griffith theory to his concept of stress intensity factor. He said that yes, at the point of onset of crack extension, the extension takes place when that energy availability per unit crack extension is a critical value, and that value is actually K1 square by E, and Griffith's energy is that, so that is G. So Griffith energy is given by stress intensity factor, the crack tip stress field parameter K1, which is called stress intensity factor, not stress concentration factor. That is the parameter which is actually appearing as a term, constant term, amplitude term, K1 by root 2 pi r into sine theta and r function. So this K1 is the stress intensity factor at the crack tip. It depends on the external loading at the crack geometry, and it is now also related to that at the point of onset of crack extension, the energy release rate per unit crack extension is related to this parameter. So therefore, you see that Griffith theory of crack extension is associated with a critical quantum of energy release rate is equivalent to saying that crack extension is actually associated with a critical stress strain field around the crack tip. It's not stress strain at a point, but it's a field. See, that concept of actually single person actually dominance is now nullified. It is actually what you call that democratic view, like that. It is not the stress at a point that is important in the case of failure of material. It is the distribution of stress and strain over a zone around the crack tip. So it really, crack extension is associated with a critical stress strain field around the crack tip. So that democratic view of the actual material failure is given. by this theory. So that's how it became a new way of understanding material failure, and it also overcomes the question that it does not actually give any importance to the question of stress at a point. It is stress around a zone, and that's what it is. And therefore, you see that for all the three modes of crack extension, that is tensile mode of crack extension, shear mode of crack extension, torsion mode of crack extension, for each of the case, Griffith theory was related to Irwin's theory. Like here, that for all the three modes, he gave the final position that for the mode 1, this G subscript 1 is related to K subscript 1 at the point of onset of crack extension. This is therefore GI reaching a KIC is a critical condition for crack extension. So similarly, we also established that G2, mode 2 strain energy release rate, is related to K2 square by E, where K2 is the mode 2 stress intensity factor, and mode 3, G3 is the Griffith's energy, and K3 is SIF, K3 is related to strain energy release rate. So that's how if somebody says that Griffith's condition is G equal to G critical, then according to Irwin, it is K equal to Kc is the critical condition. So that's how they became interrelated, and therefore it gave the sound understanding that it really is it is validated from the point of view of energy and the point of view of also stresses and strains. And Griffith theory, that Griffith theory was difficult to apply because calculation of energy is very cumbersome. Indeed, I have given you the calculation of energy that is released very simple way, but then in fact the mathematics that is involved in calculating the energy release rate is very involved. It's a very difficult mathematics, and therefore all that problem made it difficult to apply fracture mechanics to practice. But after the evolution of this Irwin's theory of stress intensity factor, the application of fracture mechanics became very easily possible. And indeed, after about 1960, all these developments actually took place, and lots of calculations, lots of mathematics were done to find out the stress intensity factor of components of different shapes and size. And in fact, like stress concentration factor based design, they made it imperative that there must be availability of stress concentration factor, and therefore lots of handbooks were written and published. And in the case of fracture mechanics, after the evolution of the concept of stress intensity factor in the 1960s, people started considering varieties of components and their loading, and then they also actually gave rise to solutions for the utility in design stress intensity factor handbook. So there are 4 or 5 stress intensity factor handbook which are widely used in practice. So that's how the stress intensity factor concept became very important and also widely applied, and it has actually some importance. So let us just try to take it up. Importance of K approach. You see that first of all, this K stress intensity factor can be easily determined than G, which is difficult to calculate. So that was another stumbling block in applying the strain energy release rate concept. And for mixed mode loading, the solution for K can be also easily obtained, and therefore that also made it easy to apply the stress intensity factor approach to understand mixed mode problems. And for mixed mode loading, the stress fields, it is also something which can be taken up. So if you have a problem involving more than one mode, then the stresses are obtained by just simply superposing the stresses in the individual modes. Like Sigma x in a mixed mode problem is nothing but sigma x in mode 1, that's subscript 1, sigma x in mode 2, and if third mode is also there, you can superpose that, and therefore you can calculate the stresses in the mixed mode also very easily, routinely. And other point also, which has some importance, that fracture conditions in terms of K ensures availability of both stress and energy conditions. I know that fracture condition in terms of K ensures availability of sufficient stress and strain field around the crack tip to break the atomic bonds, plus availability of enough energy for the creation of new surfaces. So you see that in a sense, fracture condition in terms of K, it is inclusive of both necessary and sufficient ones. Necessary condition is actually that it should have sufficient stress field and also availability of energy. So the energy condition and stress condition necessary and sufficient condition. So fracture in terms of K ensures both necessary and sufficient conditions, but in the case of energy-based criterion, it does not ensure the both conditions, and therefore they are actually lacking. But then K condition is actually necessary and sufficient. So that's why K is much more strong criterion, is much stronger criterion than G-based criterion. Look at these examples. I think I wanted to show you these examples. Look at that, a linkage. If you think of a linkage in a mechanism, it is longer, it has longer dimensions in the length direction, and a crack is perpendicular to the loading direction. This is mode 1. Right? In the case of a beam, look at that. The second example on the right, if you have a beam and a crack like that, you see that if you draw the shear force and bending moment diagram, at the crack location there is both bending and shear. So that bending is trying to open up the crack faces, so that gives rise to mode 1. And then that shear force which acts in that cross section, if you draw the shear force diagram, shear force is constant all along the length, and therefore it is constant, and therefore two parts of the component just actually, if you separate them at the crack plane, the right one is going up and left one is fixed, so therefore it is mode 2. Crack faces are moving parallel. So that is mode 2 example. And then if you think of a, let's say, pressure vessel which has both circumferential and longitudinal joints, the joints are having possibility of containing crack, and this crack can be in the weld direction itself. So if you have longitudinal weld, then the pressure which is acting inside the vessel, that is going to give rise to both hook stress and axial stress. So the crack which is along the longitudinal direction, so that's trying to be opened up by hook stress, and therefore that is mode 1 crack. And if you think of the other crack which is in the circumferential direction, if it is closed cylindrical vessel with internal pressure, then the pressure which is acting at the two ends, they are trying to actually separate the crack on the crack plane, and therefore that is actually again mode 1 crack. So longitudinal crack is subjected to mode 1 loading because of the hook stress, and if it is circumferential crack, then it is loaded in mode 1 because of the axial stress. So therefore please note that. This punching blanking, look at that. Punching blanking. So there you have the punch at the bottom and the sheet metal at the center and the punch at the top. So when you are trying to press the punch, it is trying to actually, the edges of the punch is getting eaten up, or it is getting pushed into the material, and that gives rise to finally cracks near the tool edges, and those cracks finally move in the vertical direction and meet each other to separate the material, and that is what is punching process. So punching is a process, is a mode 2 type of crack propagation, and that is how it is. Now look at this. In the case of the next example, let's say beam which is horizontally located and we have a vertical load. Now tell me, what is the type of loading on the crack plane? Can somebody answer? What is the type of loading on the crack plane? Yes, participants, please just try to open up. Any guess? None? See, you remember shear force bending moment diagram? So if you consider this is a rectangular beam, and if you try to plot the shear force, shear stress variation, let's consider that this beam is a beam of rectangular cross section. So if you try to take a section slightly on the left of the load plane, so you are going to have some bending moment, the shear force will be there of magnitude P. And that P is going to give rise to shear stresses in the horizontal direction, horizontal plane. At every plane, there will be shear stress. Shear stress is going to be zero at the top and bottom fiber, and it is going to be maximum at the center, parabolic variation of the shear stress. So if this crack is lying at the center line, you see that along the center line, the shear stress is going to be maximum. That means if you try to consider two segments, this beam is split into two segments, just about the center line, if you just consider top half and bottom half. So because of this loading, those two halves are trying to shear over one over the other. That means if you try to consider that the glue joint at the center lines, that glue line will be subjected to shear stress. And that is actually, that crack will be extended by shear stresses along the center line, and it is mode to component, mode to loading on the component. So that's how it is very important. And look at the gear tooth. So if you have the loading on the gear tooth, so what sort of loading is there on the crack plane? Yes, please, somebody should try again. What is the loading on the crack plane or on the crack?
It will be shear, sir.
Yeah, shear is there, but at the same time, a bending moment.
Bending moment will also be.
That is also there, right? So it is mixed mode. You see, it is, if you just consider that as a beam, and it is like a cantilever beam from the root of the tooth, see that P, which is acting at a distance, will give both bending moment and also shear force. And therefore it is mixed mode problem. So that's how it is. And let's see the next example. Look at this left example. What is this? I think I want some answer from some people here.
The thin plate subjected to tensile load and a shaft subjected to torsion load.
Torsion, yes.
Yeah. No, left one is what? What are the modes you think of it?
It will be tearing mode, sir. Tearing mode.
Okay, only one?
Sir, it is mode 1 and mode 2.
Correct. It is right. That's how it is. If you just think of that sigma acting, it is at an angle with the crack plane, right? So you can actually break it into a component parallel to the crack, another component normal to the crack. So therefore that crack, the load component which is parallel to the crack, that gives rise to shearing mode, mode 2. And the component which is perpendicular to the crack, that will give opening mode. So therefore it is mode 1 and mode 2 combinations. And whereas the last example is pure, it is mode 3, shearing, which is actually called shear torsion. See, that crack is trying to, the crack plane is going to shear up and it will give rise to torsion. So these are actually, varieties of problems that will be faced in design, and then one has to handle them. So that's how it is. So this, I think, is what we probably, if you have any queries, questions, please raise. So we have time, at least another 10 minutes we can spend on the question and answer session. If you have anything, understanding, questions, please try to understand. So finally, what I'll sum up, I have tried to actually give you the developments that have taken place leading to development of damage tolerance concept, and then its basis is fracture mechanics, how it has evolved. And the concept is really from the very basic of material science, but then gradually the development was having problems at every stages, and those problems or queries has been answered, and gradually all the queries and questions were solved, and finally it was developed into a subject which is not science, which is more of actually engineering, and that development has taken place, and it has given rise to very rational basis for handling the associated modeling, plus at the same development of material data or collection of material data, and using them how the design can be done. So that's how it is, and it has been able to answer many unsolved questions related to classical design. Firstly, that it has made possible to use materials with defect. It has made possible to answer safety and reliability of assess safety and reliability of a component with damage in it. It has made possible to calculate the degree of safety available at a particular stage of the system in service. And then, I just wanted also to add at this point, although it will be taken up later probably. See, the question is that when you are trying to think of a component with cyclic loading, its life, that means how much life it has spent and how much it has been left to it, those are questions which need to be answered. And in fact, this fracture mechanics has made possible to do that rationally. So that is a very important thing. That nowadays in every industry, whether it is your motor vehicles or aircraft, everybody is trying that we can guarantee life of this much period. How is that possible? See, earlier days we had endurance limit, fatigue limit based design. That simply said, yes, it's gone. If this much time is gone, it is gone. But then now it is possible to say that yes, okay, it has actually damage in it and it is about to be rejected, but then we can have a relook at, we can do calculations to find out how much life is left and how much of degree of safety is available at a particular instant of time. So this is something very fantastic. In fact, I always keep telling students, that one issue, and look at that, aircraft companies, this travel companies, transporters, they have vehicles, they have aeroplane, and which is now detected with a crack and it is grounded. And if you think of it as a passenger aircraft, and just grounding it for some time means how much loss. And then the owner of the company would like to ask, can you give me some way to really get it going, let's say about a month or a week, and we can probably ground it that much time and then arrange for its replacement. Or maybe can it actually go even with that defect for another time, for another actually span of time of few months or so. Then you see how much of relief that they can really go on using it and without any danger, and it is such a utility. Similarly, you think of it, an atomic power plant, then when Tarapur was first in the 1960s, they detected that its life is gone and therefore we have to really have a new plant installed to overcome the deficiency in power generation. But then you see that the atomic energy, they started putting up questions that can we really at least answer that how much time it can still go on so that we'll have some time available for its replacement. So that they did the calculations, and in fact with the scientific calculations based on the structure mechanics type of calculations, they came up that Are Baba, it's possible we can go on using it for another 10-15 years. So Tarapur's life was actually extended by 15 years. You think of it, how much of money involved in it. So that if the plant is going on 10 to 15 years, how much of money is being saved and how much of great utility it has. So that's possible. You see, that's the way Tarapur, the point is that that crucial component that was actually most crucial and which was at the root of the whole danger, they analyzed and they did the replacement and did the calculations. They found out the time that how long it is going to be safe, and subsequently they replaced that component the way the way it could be actually used without any danger. That was also announced, and therefore that was extended. So therefore you see that how much of money is being saved for the national exchequer. So these are very important issues. The aircraft company, if you say that my fleet can still go on with this much of safety for this much time, and means actually so much of money being saved and earned. So this is how it is. So it has made possible all this because of this damage tolerant design or fracture mechanics based design. So that's how it is. See. That's how it is. It is very important, and to know the subject, and obviously the subject has developed to a substantial extent, and it has been the basis for now on. That from the time this damage tolerant concept came up based on this Griffith's calculations, it has become actually a boon to the humanity, and it has been used left and right for exploitation. Yes, so that's how it is. So I think that's it. If you have questions, please raise, and then we have still 5 to 10 minutes. We can spend 5 minutes, another 5 minutes. You don't have any question. Some of you must be doing research, and therefore you would have questions. Is it that if you want to learn this subject?
Sir, good morning, sir.
Good morning.
This is Suresh Kumar, sir, from Ramco Institute of Technology. Actually, the Griffith theory is used for brittle material. Sometimes if the brittle material, sometimes BCC, it's a brittle material. Sometimes if it goes, you increase the temperature, the slip system may change. So slip system change, that will cause the deformation of the material. Even brittle material also having some small amount of deformation prior to the fracture. So in that case, what kind of analysis we need for analysis need for the crack tip?
Crack safety. You see, that's what it is. Basically that. Then in that case, that plastic deformation capability, we have to assess, and then modified Griffith theory, which is nothing but Irwin or one modification. That is the simplest way to go about. Irwin or one modification. Irwin actually was purely brittle, but then Irwin or one modification that took care of this plastic deformation, and therefore it requires that calculation of gamma p, specific plastic deformation energy.
Okay, thank you, sir. Thank you, sir.
Yeah.
Sir, one participant, Mr. Gururaj, has a question. He has written it in the chat box, but I request Mr. Gururaj to ask the question directly to Professor Maiti.
That's right.
Sir, I'm Gururaj from Ramco Institute of Technology, sir. Sir, already you have explained the Griffith theory is for brittle material, and then the Irwin modification is applicable for ductile also. So we have to add that plastic energy, right?
Yeah. Plastic.
So what about the metal matrix composite material, sir? So we can apply the Irwin model to that metal matrix composite material, sir?
Yeah. It is.
So this
is obviously you see that nowadays all the airborne structures, they are composite materials. Obviously, fracture mechanics has abundantly been applied for this type of applications. See, layered composites and composite materials, obviously it has been applied. So you have a different way of calculations there, because the crack also is not that simple. It goes actually cocoid, and therefore all those things have been possible to take care of, and development has taken place.
Okay, sir. So
Yeah.
based on the application, we have to fix the model. Isn't it, sir?
Which is that? Sorry, beg your pardon.
Sir, based on that application and the mixity of that reinforcement particles, we have to fix the model. Isn't it, sir?
Yeah, it is. You see, I mean, I give you a simple example. You think of it that you have layered composites.
Yes,
Okay?
yes.
Or even actually, let's say, think of it bimaterial.
Yes.
Bimaterial. So if the bimaterial is there, then calculations are being done.
Okay. Okay.
Yeah, you
thank
see that timber is a composite, timber is a composite. It
Yes.
is actually mostly, it is bidirectional. It's longitudinal and then the radial directions are actually two important directions, and third direction is tangential. And even actually in the case of these materials, the energy required for tag extension in the direction perpendicular to the longitudinal direction, then perpendicular to the tangential direction, perpendicular to the radial directions, they are all different. Timber is a composite material, typical composite materials. Its toughness, the toughness of timber in the longitudinal direction, in the tangential and in the radial directions, they are all different. They are also being studied, and then obviously the crack propagation in those cases also are being studied, and it has been understood to a substantial extent. Composites is of course is a vast area, and where fracture mechanics has given a tremendous contribution and also help in exploitation of composites.
Okay. Thank you. Thank you, sir.
Yeah, there are actually papers, books available, composite fracture books are also there, and they are more involved. But it is actually understood that obviously without that, this development of this in the design wouldn't have taken place. Thanks.
Okay, sir. Thank you. Thank you, sir. Thank you.
Sir,
Yeah.
at macroscopic level,
Yeah.
can we treat metal matrix composites as isotropic?
See, macroscopic level.
Yeah.
Generally, what happens that concept has to be different, because generally the stress-based design that we consider, they are actually macroscopic idea.
Yeah.
So it is not microscopic. So microscopic level, they are, then in that case, there are models which are lattice-based model, grain-based model. So they are different. The sizes are different, and the approaches are also different, slightly different. But then the stress-based design is principally actually a macroscopic design, macroscopic model-based design. So therefore, all that we were talking today in the morning, it is all based on actually macroscopic design.
Yeah.
Because material scientists, they would like to actually go for atomic model, then grain-based model, crystal-based model. So varieties of levels are there, and the stress calculations are going to be different.
Yes. Okay.
Yeah.
Sir, on behalf of the participant, I want to just put a general question. That many of them are listening to the discussion on fracture mechanics for the first time, maybe.
Yeah.
So I want you to elaborate the idea of stress intensity factor little more.
Okay. You see that when you consider that obviously stress analysis you have studied all through your life, and you know very easily about the concepts. And herein, in the case of fracture-based design, it is again that stress field which is important in the designing of a component, or trying to actually specify the failure condition of a material. So in doing so, the stress field around the crack tip had to be analyzed, and it was analyzed, and finally it was found that that stress field has a typicality, that it is a field which is having series of terms. The first term is most dominant as radius or distance, radial distance tends to 0, it becomes almost infinity. So it cannot be actually talked about one cannot talk about failure in terms of stress at it. I think please listen, all of you, that when you try to talk about fracture mechanics, the stress analysis gave rise to the condition that the stress field around the crack tip is an expression involving infinite number of terms, where the first term is actually 1 by root r, second term is r to the power 0, next term is r to the power plus half, and so on. So common difference is half. So therefore, as r tends to 0, what happens that all the terms consisting of positive exponent, they are 0, then the constant term, and then the first term, which is 1 by root r, that tends to infinity. So therefore, in the presence of a crack, stress field is actually very complicated in that matter, for that matter. But then the stresses at the crack tip, near the crack tip, is infinity. So one cannot really talk of failure in terms of stress and strain as we used to think about. But Irwin could show that obviously, that energy required for crack extension is fortunately related to that exponent of the multiplier of the first term, which is proportional to r to the power. So that is called stress intensity factor. As your loading increases, that intensity factor increases. As loading decreases, that decreases. So therefore, at least commonsensically one can expect that as we increase the load, we are trying to increase the gravity of the loading at the crack tip, and that is communicated by the term stress intensity factor. And at the same time, that term is also something which could relate to, as crack extends, the amount of energy that is available for crack extension is given by that term. You see, this is something blessing in disguise. That term multiplier, so it is a multiplier term is called intensity. It intensifies. Load increases, that increases. So that's why it is stress intensity factor. And as the critical condition is reached, he also showed that this intensity factor reaches a critical value, thereby meaning that critical quantum of energy is available for crack extension. So this stress intensity factor has importance, that it gives you the understanding of stress and strain around the crack tip, and the quantum of energy that is available for crack extension. And also, it is actually not that it helps you to overcome the concept of failure in terms of a value of stress and strain at a point, but a region of stress field around the crack tip. K, in fact, it conveys the idea of a region of stress and strain around the crack tip. So it gives actually domain. It's not actually a single point, but a domain around the crack tip. How much of gravity of loading is there, it is conveyed by stress intensity factor. So therefore, in that sense, it is much different. It gives the idea, I say that generally it gives the idea of democratic government. It's not that, dictatorship. It is not that dictatorship by a single fellow. It is actually distribution of, it is importance of a group of people, group of points that is there. You see, that's why it is stress intensity factor, and it has tremendous importance. It does actually, it's a new way that it is the stress field, not stress at a point, stress field around the crack tip, and it also conveys the idea of energy available for crack extension as it extends. That's all.
Sir,
Yes, sir.
sir, is it, sir?
Yes, please.
One more I think clarification is, sir, that stress intensity factor, how far a difference from the notch sensitivity factor, sir? Notch sensitivity factor, we heard it in.
No, notch is having a finite radius, whereas crack has actually zero radius.
Okay, sir.
Okay, please, you understand? It is just like that, you cut with a razor blade. So you just think of it that, you are cutting a paper by a razor blade. So it becomes actually zero radius at the tip. Whereas notch means actually it has some radius at the tip. That's why it is stress concentration factor at the tip of a notch. So it is the situation more prone to failure because with a tip radius 0 means stress is already infinity. You see, you cannot talk in terms of stress at a particular location.
Sir, out of curiosity, I'm asking about how when you consider the brittle material, how the crack speed of crack, how fast it crack growth propagated.
Oh yeah, that has been calculated.
Is there any formula is there, sir? Is there
Yeah,
formula?
this is there. Elizabeth Joffe, so she has given us crack speed. Yeah, it has been calculated. Crack speed.
Okay.
Obviously, you see that crack propagation speed is also going to depend on, rate of input of energy, all those things. Dynamic fracture mechanics deals with that. Dynamic fracture mechanics deals with that speed of crack progression.
Thank you, sir. Thank you.
Thank you.
Thank you very much, sir. It is 11 o'clock. All the participants, I am sure, have enjoyed listening to your lecture and have benefited from the basic concept of stress intensity factor as a new parameter in design strategy and the associated discussion which has been made very interestingly by you. With this, I would like to actually announce that the first session is over. Participants, the second session will start at 11:30. So all of you are requested to join in the second session with another link which is provided on our WhatsApp group as well as it has been communicated to you through email. So thank you very much all. We will meet again at 11:30 and please join with the second link for the session number 2. Thank you very much. Thank you, sir.
Thank you.